So kind of pick up where we left off. Still kind of doing a little bit of review. We'll kind of jump in to what maybe looks a little bit less like review, hopefully by the end of today's class, for sure on Thursday. So one thing we'll keep using is this review of statistics do file. Today, the data set, it's going to be from last week. I thought we might get to it. We didn't quite. It's going to be this election data set. Okay. So make sure you're going to have those downloaded to your OneDrive. Hopefully you did that last week because we're going to use them last week, but that's kind of what we'll be using. If we get there today, probably not, but for sure Thursday, we'll start using this new do file and these new data files, right? So make sure you're getting it every week, downloading the do file and the data files from that week, making sure they're in your OneDrive so we can access them. If you're still having issues with that, a couple of you stopped by last week during my office hours. I think we got them all ironed out. A couple of you wasn't sure, but we ended up working out okay. I've talked to the help people. I think I understand any issues that might arise now in terms of adding an account to your OneDrive. Some of you, I think that's the issue. So I should know how to do that both on iOS and Windows now. But we'll kind of just jump into things. So before we do, just a couple of things to kind of mention. That first problem set is up there. So you should be able to kind of start working on that in Stata based off of what we've done. I think after today, we'll have covered everything you need to complete that entire file. So that's set to be due what? The 6th, which is what? Next Thursday before class. So, hopefully you've started it. If not, I would start in that early. These will take you some time, okay? I wouldn't expect to be able to do these in an hour. Maybe for some of you, if you've already had some experience with Stata or data management programs, but most likely it's going to take you a while, okay? You'll also see, I'll probably just drag it to module 3 since that's kind of where we're currently at. I'll put a quiz up after today's class. The material that you would need to study for it, or kind of those sample questions. So I'll have that set to be due basically a week from today. So we'll have covered all the material you need to answer every quiz or question on that quiz after today. You could have probably already started reviewing for it. We've covered the majority of it already. But after today, we'll gotten through everything. It'll be due a week from today, right before we start class next Tuesday. Okay, so you'll see that pop up after class. Other than that, any questions for me before we kind of jump into the slides for this week? Okay. All right. So I might go through this initial stuff a little bit quick. Hopefully it looks familiar. So do we remember this terminology of the critical value approach? Right? So one thing we talked about last class is we ultimately want to know where the population mean is usually, but all we have is sample data. Now we know certain things about that sample distribution. We said that sample distribution, if we're thinking about our sample means, it should be normally distributed around whatever the true population mean is. We often don't know this, so we've got kind of an assumption for what that value is. Right? We then said the variance of this sample mean distribution. We kind of went through that little Stata example where I proved it to you with data, but it's basically going to be whatever the original population variance was over our sample size. Now we said we don't have, well, we have sample data, we don't know the population variance, right? So often we take our best guess of what that is using our sample variance here. Right? We can then turn any sample mean value that we see into a standardized value. So how do we do that? Well, we talked about z-scores a little bit last class. I think I, at the very end, introduced the fact that if we don't know the population variance and all we have is a sample variance, when we standardize the variable, it's not coming from a standard normal distribution. This was this different set of distributions we talked about, which was the student t distributions. Right? So what is that standardized t value going to be? Well, it's taking whatever sample mean we see, subtracting what we're assuming the population mean is, and then dividing by, well, here, anytime you standardize something, you subtract the mean and divide by the standard deviation of that statistic. Well, for us, if we know the variance, the standard deviation would just be the square root of that. Okay. So we're going to come up with these things once we standardize our different sample means, which we'll call test statistics. It's based off the sample we took. Our sample mean is this many standard deviations away from what we're assuming that mean value is. Okay. So we've got a couple different types of tests that we can do. And I'll come back to this in a second. So if you didn't get it all written down, it'll be back up here in a little bit. So what we're going to do is say, okay, we're going to make some assumption, right? We're then going to say, if we see a test statistic that is a certain number of standard deviations away from that assumed true value that we had, we're okay rejecting that assumed true value because we found sample evidence that varies from it a lot. Right? Now, how far away is far enough? Well, that's what we're going to kind of talk about. But just to kind of, summarize here, we've got 3 different types of tests we can do. One, we'll call kind of a greater than, or I'll often just reference it as a right-tailed test. We're only interested if we find sample evidence that's above the assumed true mean or to the right of it. Left-tailed test, we're only interested if we find a sample mean that's below or to the left of our assumed true value. The one that we're going to use the majority of this semester, with the exception of a couple of statistics, is this two-tailed test, which is evidence on either side of the mean goes, on either side of the assumed true mean goes against our assumption. Doesn't matter if it's higher, doesn't matter if it's lower. It's just different than what we assume. So these two-tailed tests are going to be often what we use. I've got it kind of written out mathematically here, exactly when we're going to reject, but I think I'll draw it out to make a little bit more sense here, okay? So I said, I can turn any of these sample means into a standardized test statistic, okay? So what we're going to do, and I'll show you a right-tailed test example first. Actually, yeah, I'll do a right-tailed test. So we're going to have this student T distribution. If I turn the assumed true mean into a test statistic, what should it always have a test statistic of? How many standard deviations away would the assumed true mean be from the assumed true mean? 0. So I'm then going to say there's some threshold. We'll talk about how we find it in a second, but there's some number of standard deviations away that if I go any further away than that, it's probably very unlikely what I assume to be true is in fact true. Remember, the height of this distribution, kind of what's on our y-axis, represents probabilities. In a way, we'll talk about, it's a little bit more complicated. We're interested in the cumulative probabilities, but our y-axis is representing like these are more likely, these are less likely for us to see. So there is going to be some critical value, right, that we're going to say, look, if I see anything that's more standard deviations away from what I assume to be true than this number, we're going to call this our rejection region. I'm okay rejecting what I assume to be true if I see sample evidence that's even further away than this, because the likelihood I would see that is really low, right? So for example, let's say I assume that the mean is 50. In fact, I'll color code this, right? And I see a sample mean, I don't know. So let's say I have, I see a sample mean of, I don't know, 100. I turn that into a test statistic, and I end up seeing that this is a test statistic that is larger than this critical value I set. We haven't talked about how we determine the critical value yet, but just this is the idea. If I turn that sample mean into a standardized value, and it's a t-value, a test statistic, that is greater than my critical value, it's in my rejection region. What's likely true is what I assume the mean to be is not in fact the mean. The true mean is likely somewhere over here, right? Closer to the sample I found. So I'm okay rejecting if that test statistic is anything greater than my critical value. Now, that applies to a right-tailed test. I'm not going to draw every single one, but you could do this for a left-tailed test and a two-tailed test. I guess I'll do a two-tailed test. A left-tailed test, everything will be the exact same. It's just that now I'm interested in things that are below, right? So here, well, I'll hold off on the two-tailed test. So ultimately, what we have, I'm saying that the critical value is greater than, I'm saying if the test statistic is greater than my critical value, I'm okay rejecting. If I flip this and all the negative values are negative, well, then technically I need a test statistic that's a larger negative value than my, so I actually need a value that is less than. So one way that we would say we always reject is if the absolute value of this test statistic is greater than the absolute value of my, that way it doesn't matter if we're looking at a left-tailed, right-tailed, or even a two-tailed test, we'll always be making the correct rejection decision. Okay. I think it's easiest to think about it as a right tail because positive values are easier to kind of discuss. If negative values, right, a larger negative value is actually being less than. So we'll just look at the absolute value here. Okay. So where am I getting these critical values? Okay. So once again, we'll set this up. Let's do, I think I have in the slides a right tail test. So let's do a left tail test. Okay. I'm going to say, okay, look, there's going to be a threshold value that I want to set where if I see that my sample evidence, my sample mean is a test statistic that's anything less than this value. So in fact, my critical value here would always be what? If I turn the assumed true mean into a t-value, it should be 0. So anything to the left, this critical value should be negative, right? So if I see a test statistic that's a larger in absolute value negative value than this critical value of set, I'm okay rejecting. Why? Well, I know that, let's for example say I go, see if I can, which ones I can remember from off the top of my head. I think it's approximately, and I'll use this value. Every student t-distribution would be a little bit different. For the sake of what we're doing in this class, we can always use the standard normal values or the z-table to kind of approximate because we're going to be dealing with pretty large sample sizes, okay? So my critical value of about 1.29, negative 1.29, if I look this up in my table, what I'll see is that the probability I see sample evidence, right, that's more than 1.29 standard deviations below what I assume to be true, or even further, it's the same number of standard deviations. It'll always correspond to the same probability. So the probability I see something 1.29 standard deviations below the assumed true mean, or anything to the left of that, will always be 0.1, right? So you can kind of see this is like a benchmark value. A probability of 0.1 means that there's the likelihood, the percent chance that I saw something more than 1.29 standard deviations below would be about we've got to be able to go from probabilities to percentages quickly. Yeah, 0.1 is a percent would be, it's about 10% likely, right? So it's a nice benchmark cutoff value, okay? So this is going to be a number we see pop up a lot, right? If I see a test statistic that's anywhere to the left of my critical value, what's the probability I saw that test statistic or anything even more extreme? That probability has to be less than what? 10%, or the probability to be less than 0.1. Okay. So anytime I have a critical value that's less than the absolute value of my test statistic, I know that the area to the left of my critical value, which we're going to end up calling alpha, has to be greater than the area to the left, or if we're doing a right tail test, the area to the right of my test statistic. So the area to the right of my test statistic, we're going to call that our p-value. So anytime this is true, this p-value, this red area, would have to be less than this alpha threshold that we're setting, right? I mean, if this area is 0.1, any test statistic over here, I'm just making that area smaller. So whenever I have a test statistic greater than my critical value in absolute terms, that p-value will always be less than this threshold alpha I set. I'm using 0.1 here. You can set different values for alpha. In fact, what we generally will do is compare to 3 benchmark values, which is usually an alpha of 0.1, 0.05, and 0.01. Why? What percentages will those correspond to? 10% likely, 5% likely, 1%.
Can you just go back? What does the red area describe?
Yeah, so this red area is going to represent the probability that whatever sample mean I saw, when I turned it into a test statistic, the likelihood I saw a sample mean this far away from the assumed true mean or something even further, that's what this probability represents. The probability I saw a sample mean this many standard deviations away from the assumed true value or something even further. And I use this word of further, that way it doesn't matter if I'm looking at the left or the right, right? It's not smaller, it's anything even further to the left, or if we're doing a right tail test, further to the right.
So in this case, it would be more than 1.29 standard deviations away.
Exactly. Yep. Any questions on this idea? Is this looking familiar, hopefully? Somewhat. You might be going through a little bit quicker than you did in 370 or your equivalent. So a lot of these slides, I probably have already drawn something for, but the slides are kind of like if you miss class, I guess. That's for behind me. So here I had a right-tailed test, and I chose a different threshold, right? Here I said, well, I only want to reject what I assume to be true if the likelihood of what I saw is anything smaller than what percent? Alpha of 0.05, that represents a probability, so anything less than 5%, right? Anything less than 5% likely for me to see. So I've got a right-tailed test here. Now, once again, these student t-distributions, technically the value would change depending on our sample size. We're more than likely going to use our nice standard normal approximations here. So 1.29 corresponded to that alpha of 0.1. Alpha of 0.05, well, in order to get a smaller area in the tail, instead of going 1.29 standard deviations, I'd have to go a little bit higher, right? A little bit higher. And sure enough, 1.65 gives me that desired kind of threshold alpha in the tail there of the probability of seeing something 1.65 standard deviations away from that assumed true value, or anything even further is about 1.65 standard deviations. Okay. Now, if I take a sample, I calculate my sample mean, skip ahead here for a second. There it is. I turn that sample mean into a test statistic. If my test statistic falls to the right of 1.65 here for my right-tailed test, anything more extreme, it's in that rejection region, I would reject whatever I assume that true mean to be. Right? If I find something that's, say, like 0.5 as a test statistic, is that going to be in my rejection region? No, right? So there, that would be something where I fail to reject. What I assume to be true, I didn't find strong enough evidence to suggest that it isn't true. Right? So I'm not going to change my mind about what I assumed. The only time I change my mind is if I find sample evidence that goes against what I assumed enough to where I'm okay rejecting. Okay. Any questions on this before we keep moving here? So I have a summary here, but just to kind of point some things out. So when I'm looking up these critical values, for instance, if I had a left-tailed test, what would the critical value that corresponds to this alpha of 0.05 be? Negative 1.65. It's a symmetric distribution. So if I want the same probability, it's just that now I'm not interested in something that's this many standard deviations or higher. I'm interested in this many standard deviations or lower. It's going to be the same value, but negative. So if we look at my summary here, when we have these kind of greater than or right-tailed tests or less than or left-tailed tests, the values that we find, these kind of standard normal approximations, same value, just for left-tailed tests, they're negative. Now, these two-tailed tests, where am I at? There we go. We haven't talked about those yet. Why are these going to look a little bit different? So for a two-tailed test, and this is what we'll use more often than not in this class. Excuse me. This is going to be, we have some assumed true value. That would be a kind of standardized value of 0. Here, I don't care if the sample mean I find is above or below that assumed true value. It goes against it. Right? I don't care if it's above or below. Well, if I still want to set these threshold alphas, for example, of 0.1, I want there to be a 10% chance that I saw the sample mean I did or anything more extreme. Well, if I don't care about what side of the distribution it's on, let's say I see something that's over here, right? And the probability, so we were just using this, 1.65, that I see something 1.65 standard deviations above or any further, that area is 0.05. Well, I'm only taking one sample, right? So I saw this sample mean, I turned it into a test statistic, and then, this is the probability of seeing that many standard deviations above or anything further. Well, what would it have been equally as likely for me to see from one sample? If I found something 1.65 standard deviations above the mean, if I were to take just one sample, it would have been equally as likely for me to see something that far below the mean, right? Now, when a two-tailed test, if I don't care about which side of my assumed true value it's on, both of these go against that assumption. Before, if I just wanted to know, is it above a certain value? Well, when I found something on the left side, it actually supported my assumption. I was only concerned with one side. So for these two-tailed tests, just because this is what I saw from my sample, I know it was equally as likely for me to see something that many standard deviations below the mean or anything even further away. Right? So when I'm trying to determine these critical values, I don't need the critical value that gives me alpha in the tail. I need the critical value that gives me, well, if there's 0.05 here, what would be over here? Some 0.05. So I actually need the critical value that gives me half of alpha on each side, right? Or in each tail. So inherently, instead of having 0.1 in this tail, I'm going to have 0.05. What are my critical values at the same alphas for a two-tailed test? They're always going to be a little bit larger in absolute value, right? Because it's not just one side of the distribution now, it's both sides would go against my assumption, right? So when we're looking at the summary table, those same benchmark 10, 5, 1% levels or probabilities of 0.1, 0.05, 0.01, for a two-tailed test, I'm going to need a larger value. And I'm not just going to have one critical value, right? I care if it's on either side. So notice for the alpha of 0.1 for our left-tailed test, that was negative 1.29, right-tailed test 1.29. For a two-tailed test, it's a larger value, and I have two critical values. I care if I find a test statistic that's either above or below that assumed true value. Okay. Is this looking familiar, hopefully? A little bit of from back in whenever you took 370 or equivalent. Okay. Yeah.
So for the two-tailed test, is it going to start giving you the alpha?
Yeah, generally we're always just given alpha. So for a two-tailed test, you'd have to divide it by 2 and then know that's the area you want in each tail. So let's see here. I kind of have this test set up, like the steps that you would use to do what we call kind of a critical value approach, right? When doing hypothesis testing. So the first thing I'll do is turn my sample mean into a test statistic, right? I'll then, once I have that test statistic, draw out kind of where my critical values would be, right? If my test statistic falls in my rejection region, I can reject what I assume to be true. If it doesn't, I fail to reject. Right? And kind of here mentioning that alpha, right, isn't our percentage format, it's the decimal. We can easily convert that into a percent the way we typically talk by simply multiplying by 100. Okay? So I think I have here, yeah, an empty slide, right? But here's kind of our steps. So what is this going to look like in practice? Just to kind of really hammer this idea home. So if I were doing this, I might have them written out a slightly different way, but this is how I would do it. It's not always going to be how it makes sense. So what I'm going to do is first figure out if I have a right-tailed test, I'm going to figure out what's the critical value that gives me a total of alpha in that tail. Okay. Whatever value that is, which I think if I did like 0.1, this was 1.29. I now know that for a right-tailed test, the rejection region is anything to the right. Okay. So I'll complete this example, but just to show you what it would look like for a left and a two-tailed test, I would do the same thing for a left-tailed test. It's just that I'm going to be looking for the critical value that gives me alpha in my left tail, right? There, my rejection region is anything to the left. I could also do a two-tailed test, in which case, no matter what my alpha is, I would first say, okay, what is alpha over 2? That's the total area that I want in each of my tails. I could then look up what value would give that to me. negative, positive 1.25. For a two-tailed test, my rejection region is now anything greater than the positive value, anything less than that negative value. Okay. So this is just like the first, you're never, usually you're going to only have one of these tests, right? You would set this up. And then kind of my next step would be, okay, I went out, collected some data, and found a sample mean. Now I know that if I assume the sample mean is a specific value, whatever that value is, it could be 50, 30, 200 million, whatever it is, right? Whatever sample mean value I find, I would turn that into a test statistic. How did we do that? We took the sample mean, subtracted the assumed true value, divided by the standard deviation of the sample mean, which we know is the square root of that sample variance over our sample size. If that sample means test statistic is in my rejection region, I can reject. If for some reason it was over here, I'd fail to reject, right? It's not in my rejection region there, okay? So for a right-tailed test, if I ever see a sample mean below what I assume the value is, what do I automatically know my rejection decision is? The only way I'm going to reject for a right-tailed test is if I have a test statistic that is greater or positive. Left-tailed test, I'm only ever going to reject if I see negative test statistics. Two-tailed, either one works, right? It's not as easy, okay? So that's kind of a summary of kind of how you would lead yourself to a rejection decision using that critical value approach, okay? Questions there? So I think I have those steps outlined here. Once again, determining the null and alternative. This is not going to be something we ultimately do a lot of in this class. I'm generally going to give that to you. I'm going to punt a little bit on this in terms of identifying. I'm going to either tell you, show you what a right and left tail test looks like here in a little bit. So you'll generally just be given this test, or like what if you're doing a right or left tail test. And for us, like I said, more often than not, we're just going to do two-tail tests. So I would default to just thinking about anything we do is going to be a two-tail test. Alpha will be given to you, right? Or you can use 3 alpha. So with the critical value approach, it's a little bit convoluted. So I want to do a test for like 3 different alphas. I have to have 3 different critical values. So approach that maybe makes a little bit more sense instead of going through all of these steps. Once again, I would probably switch 3 and 4 here. I would probably plot the critical value and the rejection region first, and then find and plot my test statistic. But you can do it whatever way. I mean, you could do it in the other order and still come to the right answer. So the other approach that's going to be probably easier for us is the p-value approach. Okay, so I kind of already alluded to this. Where was it at? We said, yeah, anytime my critical value is less than in absolute terms than my test statistic, we said inherently my p-value, or the probability I saw that test statistic or anything greater, has to be less than alpha. So if this has to be true in order for us to reject, right? We have to see test statistics in that rejection region. Anytime I have a test statistic in my rejection region, what will automatically be the case is that my p-value associated with that test statistic has to be less than alpha. Okay? So if I know that my alpha benchmark values are always 0.1, 0.05, and 0.01, an easier approach might be find my test statistic and then determine what's the probability I saw that test statistic or anything greater than that. Okay. So I'm kind of setting us up for some things we're going to do in linear regression. I'm not going to ask you to actually use those student t-tables to look up p-values. I'll have you use the approximate values from a standard normal. So what is that going to look like for us? And I forgot to pull it up, but we have that. Oh, do I have it in my OneDrive? Probably not, but that's okay. because put it under the Files tab. We're going to use these Z tables to kind of approximate. So remember, we said last class, I can look up a Z value and find the associated probability of seeing that Z value or anything to the left. So here, if I am working in reverse, I know my three alphas, right? 0.1, 0.05, 0.01. So notice, if I want an area of 0.1 in my tail, looks like I'm in between these two values. That's a Z value of negative 1.28, negative 1.29. We'll always kind of use the larger of the two, or round to kind of the large. So here, negative 1.29, which is the value I was using earlier. That's where that came from. If I wanted 0.05 as my alpha, well, what value would give me 0.05 in the tail? Looks like it's in between these two. So what? 1.64, 1.65. You can either split the difference, 1.645, or the way that I'll write these in the calculations, you can use the higher of the two, 1.65. Now, if I wanted to look up a p-value, and I wanted to do the p-value approach, so let's say I had a test statistic. I have some sample mean, I turn it into a test statistic, and I get, I don't know, 1.37, okay? And let's say, for the sake of this example, I've got a two-tailed test, right? That I'm assuming that this mean is exactly equal to some value. I don't care if I see evidence on above or below. Well, what I can do is look up this value in the table. Problem is that Z table will give me an approximation. It's always going to give me the area to the left. So if I look it up, I want to know what the area to the right is. What can I do? We said from last class.
1 minus.
Area under the curve is 1, so just 1 minus that. Right? Now, once I have this area, that's not my p-value if I have a two-tailed test. Because seeing evidence this far above the mean, it would have been equally as likely I saw that evidence but below. So how can I find my total p-value? Just take this area, multiply it by 2. Okay. So in this example, I'll go to my standard normal table. I had 1.37. Well, all these, so I scroll down. Okay, 1.37. So 1.3. Second decimal was 7. So that's what? 0.9147, right? So this area I just found was 0.9147, right? Which means to find the area to the right of that, I would just subtract it from 1. So this is going to be what? 0.0853 if I'm looking at this and doing math correctly in my head. I then multiply that by 2. I'm getting approximately what? A p-value of 0.17. Okay. This is now the value that I will use. If I just want to use the p-value approach, I don't have to look up critical values. I know that I'll reject as long as the p-value is less than these alphas that I'm setting. So in this example, is my p-value going to be rejected at any level? Is that less than 0.01? No, so I would fail to reject what I assume to be true. Is it less than 0.05? No, so I fail. Is it less than 0.1? Here, I didn't find strong enough evidence to reject my assumption at any level. Any questions on this p-value approach idea? What if instead, well, I'll show you another way of finding this that for some of you might think is easier. Let's say I found a test statistic instead of 1.78. So I could do the same process to find my p-value. Actually, no. I'm changing this for a reason. Let's say it's 2.05. Okay. I could find my p-value the exact same way, or because this is a symmetric distribution, instead of finding the area to the left of positive 2.05 and then subtracting it from 1, what could I also do? Find the area to the left of negative 2.05 So, well, negative, let's see, is this all going to fit? Not quite. Negative 2.0. Here's my second decimal is 5. So negative 2.0202, right? Because it's a symmetric distribution, I know that has to be, if that's the area to the left of negative 2.05, that's the same as the area to the right of positive 2.05. So that's going to be the area to the right of 2.05. So this is what, 0.0202. So what would my p-value here be? Well, I would still have a two-tailed test. If I multiply that by 2, my p-value is now 0.0404. Would I reject at that alpha of 0.1 or the 10% level? Well, now, yes, I would. Would I reject at the 5% level? Yes. Can I reject at that 1% level? Here we would say, no, I fail to reject, right? I found strong enough evidence at these kind of lower levels, but not at the highest. Okay. Where are we at on time? All right, we're doing good. Any questions over anything here before I kind of switch to the next topic? So I'm going to set us up a little bit to talk about confidence intervals. One thing I did want to point out here, just some terminology that we use with hypothesis testing. When I'm thinking about alphas of point, so these are our benchmark values, we would typically say these correspond to different significance levels. And the significance level is just alpha in percentage form. So this would be 10%, 5%, and 1%. When we say we can reject at a certain level, a more common terminology is going to be at what level of confidence can we reject at? So this significance level, if the probability that we saw what we saw is 0.1, right? What's the probability that we saw something that was below that or that would have went along with what we assume to be true? 90%. So the confidence level will just be our significance levels kind of subtracted from 100, right? So the 10, 5, 1% significance level, when we can reject, we're really saying we can reject with 90, 95, 99% confidence. That lines up more with how we speak, right? Because we know that if I need the p-value to be less than 0.01, that's going to be harder to find than a p-value less than 0.1, right? So when I reject, when the alpha is 0.01, I'm really rejecting with a higher level of confidence, right? I'm 99% sure that based off the sample mean I found, what I assume to be true isn't true. Whereas if I only reject an alpha of 0.1, I'm rejecting, but I'm only having 90% confidence in that rejection, right? Any questions before we keep moving here? Okay. Yeah.
Is it possible for you to have 40% confidence level?
You can choose whatever you want. As I choose lower levels of confidence, though, I mean, if I choose 1%, let's think about what that would mean. Let's say I wanted to do a 1% confidence level. So we'll work in reverse. All right. What level of significance would that be? What's the alpha? If I take a sample at random, if I had a p-value of 0.99, that would mean I would have to see something, right? Anything outside of this range, I'd be rejecting. So like, I'm almost guaranteeing I'm going to reject the null if I lower the level that much, right? So like, if you're looking at academic papers or like kind of what is respected, these are kind of our three traditional, and we'll see why here in a second. I'll try to mention something that's kind of businessy related, even though you're not in Kelly, but you're econ majors, you might find it interesting. So hold on to that thought. All right, any other questions here? Okay, so where does that leave us? So we want to talk about confidence intervals. So we talked about this p-value approach. Really, the steps to our critical value, or sorry, p-value approach. are going to be pretty similar. Like we still need the test statistic to find the p-value. It's just that instead of finding a critical value and comparing that to our test statistic, we're using our test statistic to find a p-value and compare that to alpha. Right? So we're really just kind of comparing two sides of the same coin, right? We either compare the critical value to the test statistic or the alpha that corresponds to that critical value to the p-value that corresponds to the test statistic. Right? So, well, I might skip some of this stuff, but this is worth doing, I guess. I thought we were done before we get to confidence intervals. I might come back to some of the type 1, type 2 error stuff next class. So, if I'm thinking about any level of hypothesis testing I want to do, and I'll use a right-tailed test just for the sake of, well, it doesn't matter. I can do a two-tailed test. So this would be like, what critical values give me alpha over 2 in each tail? And then my rejection regions were anything here. Yeah.
How to change the p-value to p-value.
So that's, you have to look it up in that table, right? When I was just looking that up, finding my test statistic, and then finding the corresponding area in the tail, that area in the tail, that is my p-value. So there is an equation. It's the, you can Google it. It's the probability density function, actually, sorry, cumulative density function of the normal distribution. You're not going to want to integrate that from negative infinity to your test statistic every single time. You're going to want to rely on those tables, which someone's already done that integration. But in practice, like I said, we're using the same benchmark values. So we're always going to see, you know, the exact same critical values. So in that sense, using your test statistic and comparing it to the critical values might be a little bit easier. But if you have the p-value, which moving forward in the semester, we're going to be not concerned about looking up the p-value. The p-value is going to be reported to us in Stata. So Stata is going to do a lot of the work for us in terms of it'll take our test statistic and tell us the corresponding p-value already. So we don't have to worry about using the physical tables in this class. I'm showing it to you just to give you some background. That's what Stata is going to be doing behind the scenes. It has like that table, like technically it has the formula built in and it's doing the integration, but we get to kind of skip that step. And I think we'll get there today where I can show you that. Okay. So the couple of things I did want to point out. So let's say I have this mean and I'm assuming that it's equal to some value. Okay. I know that I'm going to reject if my test statistic is in these rejection regions, right? So let's think about what's going to make it more likely I can reject the null, okay? So I know that if my test statistic is in this rejection region, I'm going to reject. So what makes that more likely, okay? Well, if I found the same sample evidence, but I did so using, so I found the same sample mean. Maybe I assume the mean is 100. I take a sample and I find that the mean, whatever the variable I'm looking at is 120. If I found that same sample mean, but from a higher sample size, is that going to make it more or less likely I can reject? Well, if I have a higher sample size, what happens to this fraction? The denominator is larger, this fraction goes. Now, if this denominator is smaller, this fraction will go. So that would make it what? More or less likely I reject. Well, technically, I could have found a test statistic here before. It's more likely it pushes it into that rejection region. So taking higher sample sizes will make it more likely we can reject the same assumed true value. Okay? And the reason why is kind of intuitive, right? If I have more observations, that sample mean should be more reflective of what the true mean actually is. Now, what if I was sampling from data that was really varied? Well, like let's say I had a huge variance and I only sampled like 10 people. It may just be the case that I ended up with 10 people that were like really far away from the true mean. So if my sample variance is larger, what's going to happen to my test statistic? Well, now this fraction, if this numerator goes up, this fraction is larger, If my denominator is larger, what happens to this fraction? Goes down. So a higher sample variance is going to actually make it less likely. And all these arrows, right, would work in the exact opposite. Smaller sample size, less likely. Smaller sample variance, more likely. I'm just kind of writing out one of the effects here. What's the other thing that could change from my sample? Not my sample size, not my sample variance. What if I find, and this one I think kind of makes sense, if I find a sample mean that's further away from that assumed true mean, so kind of think about, I'm finding this as like higher, doing a, thinking about positive values here. Technically, I should be doing everything in absolute value, but just for the sake of not throwing in a bunch of these brackets. If I find a sample mean that's even further away from my assumed true mean, what's going to happen to my test statistic? It's going to go up, which should make it more likely, right? So these are the three things that can change that'll make it more or less likely. I reject that same assumed true value, okay? Any questions over anything there? So let's go here. We'll try to get through that. Well, we'll skip the type 1, type 2 area discussion for today. So we're going to skip through these just a little bit so we can talk about confidence intervals, okay? So very closely related to hypothesis testing, especially when we're looking at a two-tailed test, is going to be these things we call confidence intervals, okay? So let's say I was looking at a standard normal distribution, and I wanted to know what two values would give me 95% likelihood I see something in between these two values, okay? That's the thought experiment. So what will end up being the case is that if I'm looking at my sample distribution, if I go 1.96 standard deviations to the left and to the right of the sample mean I see, there is a 95% likelihood that based off that sample mean, the true mean is somewhere in that range, okay? So what does this look like kind of visually, right? If I had I know what the population mean is, and I take a sample, all the sample means that I see in this range would be within 1.96 standard deviations of that true population mean, right? I know that this is what the distribution of my sample means will follow. So if I were just to take one sample, what's the likelihood I see something further than 1.96 standard deviations away from the true population mean? Well, if we go back, right, the area to the right and left of that z value of 1.96 is just 0.025. We have two tails. That means the total probability I see something either 1.96 standard deviations above or below is the probability of 0.05 or 5%. Right? So I know that even if I can't see that true population mean, if I take a sample and around that sample mean, I go 1.96 standard deviations to the left and the right, that confidence interval will include the true population mean. So think about why, right? So let's say I have the same setup. I take a sample and I see this sample mean. Well, it's less than 1.96 standard deviations away, right? This would be 1.9. So if I build a confidence interval around this by going 1.96 standard deviations above and below, my upper bound in this case would go past whatever that true population mean is. If I were to take another sample and I see this is my sample mean, well, it's about what, 1.8 standard deviations away? So if I subtract 1.96, well, now my lower bound is going to be on the other side of that true population mean. So that's going to be true for any sample mean I see in this blue area. When I build a confidence interval around it, my confidence interval would include that true mean, right? So what's the likelihood I see a sample mean in this blue area? The way that we had it set up, we said 1.96 gives me 0.05 outside of the range, so 95% likely, or a probability of 0.95. Now, there is a 5% chance that Zoom gets in the way. There's a 5% chance I see a sample mean that's more than 1.96 standard deviations away from that true mean. Now, if I build a confidence interval around this sample mean, what ends up being true? My upper bound wouldn't quite capture that true mean. So when we're building our confidence intervals, we're only ever doing it using one sample mean. But we know that in practice, if I could take 100,000 different samples, that 95% of those samples would have a confidence interval that includes the population mean. However, for any sample mean value here, 5% of those confidence intervals would not include it. Right? So if I use my sample mean to build my confidence interval, I can say essentially that with 95% certainty, I'm sure that my confidence interval based around my sample mean should include what the true population mean is. There's a 5% chance that it doesn't. Right? Now, if I wanted to build this for, say, like a 1% level, I wouldn't use 1.96 standard deviations. I'd have to use, I go back to the table, I think it's 2.58 standard deviations away we would have to go, right? So what's going to be true? If I want to say things with a higher level of confidence, in order to get the area in the tail to be like a smaller alpha value, I'm going to have to do a higher number of standard deviations. So larger confidence intervals will be, higher levels of confidence, going from like 90 to 99%. The number of standard deviations away I need to go to build that confidence interval will go up. So my confidence intervals will become wider, right? But that's kind of the thought experiment, right? We only ever usually have one sample, but if we were able to take an infinite number of samples, 95% of them would include the true population mean, 5% of them would not. And we won't get to it today. Maybe next class I'll bring in and kind of prove this to you with some data sets, okay? Yeah.
Okay, so like last time we ran like a program,
Mhm.
and you were kind of talking about if you did this a certain amount of times, is there a way we can do that on Stata, like run a program that?
Yeah, that's what I'm saying. I'll try to bring in something next class
Okay,
to even show this to you. No, you're fine. You're fine. I don't think we'll kind of quite get there today. So I have this I want to rearrange for you. I really want to get there. Where are we at? We've just got like 20 some minutes left. What's the most valuable use of our time today? We kind of already discussed this. I do want to give this to you just to kind of show you how we're going to connect hypothesis testing to confidence intervals. And then I'll show you some stuff. I want to do a quiz and also maybe some stuff in Stata. So how do these confidence intervals, there we go, line up to what we're doing with hypothesis testing? So regardless of whether or not we had a left, right, or two-tailed test, we essentially said we're going to reject if that absolute value of the test statistic was larger than the right, if it's just greater in magnitude. I'm going to rewrite this, right? This was our sample mean minus the assumed true mean divided by this, okay? If I take absolute values, don't worry too much about the math here. I'm not going to like make you reproduce this. I'm just trying to give you some support behind why. But essentially, this is the same thing as saying this, right? So if the positive value is any greater than the critical value, or if the negative value is a larger, like negative value, okay? So I'm just, that negative sign ends up being there, right? That's just a law of kind of how we write out absolute values. Well, if I rearrange this, if I kind of move things over here, right, and try to solve this in terms of my sample mean, what I'll end up doing is, okay, I'll multiply this first. That cancels out. So I'm left with what? This. And then here, okay, well, it's kind of weird to think about, but if I want to distribute this negative sign, and then I would add that. I end up with, if this sample mean is less than or more than this many standard deviations below, then essentially I'm going to be rejecting. Well, what does this kind of look like if I rearrange this a little bit? So this is going to be our hypothesized true value. This critical value corresponded to a different alpha, and here this was the standard deviation, and I say x here, sorry, of our sample means. So essentially rearranging this portion, this is what our lower bound was. All right. Now I could do the exact same thing over here. I won't walk through the math as slowly, but if I rearrange this over here, what I also end up with is if this sample mean is greater than that same number of standard deviations above the mean, then I would be rejecting. So out of this rejection decision really comes the equations for my confidence interval, right? I'm going a certain number of standard deviations above and below that sample mean, right? This is an actual value here, but really it's that like critical value that corresponds to whatever alpha we were setting, to whatever level of confidence interval we wanted to build, okay? So when we make decisions using our confidence interval, it's going to be the exact same rejection decisions as if we were to use kind of our hypothesis test, okay? So we can use either tool, right? And once we get to regression, we'll kind of see some output from Stata where we really are going to use both of these, right? We can either use the critical values, compare that to our test statistic, or we can use reported confidence intervals. And if that assumed true mean is anywhere outside of that confidence interval, we're okay essentially rejecting, right? And those decisions will always be the same. They'll always go hand in hand. Don't worry too much about this. This is just kind of to give you like the mathematical support as to why that's happening, okay? And in fact, I think the way I had it set up, I'm saying this is where like you're building, I really should have had these in place of each other, but it's ultimately the same thing. As long as I'm building my confidence interval around that sample mean, that true assumed true mean will be somewhere in that confidence interval if this isn't true, or it'll be somewhere outside my confidence interval if I can reject, okay? So what we're going to do now is switch gears a little bit. And I'm going to try to walk you through how we do this by hand. So we're not going to focus on this. I really wanted to get to this today. I think we might end on it, but I promised you 2 in-class quizzes this week. So let's make sure we have enough time to do this. And actually don't open it yet because I think I had the timing set on it not to be the end of class. I thought we might get to it earlier, but I always overestimate. So we'll have this set to be the end of class, okay? So should be open and available on the main homepage of Canvas now. The in-class quiz 1. We'll open it up. We'll preview it. I kind of had it set for last week, so we probably even talked more than what we would need to solve this. But let's say I wanted to build a confidence interval here, right? So I want to determine, based off the sample mean that I find, a upper and lower bound, right? So building this confidence interval around my sample mean, what would my upper and lower bound here be? So if I want the 99% confidence level, right? And I've got a sample of 50, I find a sample mean of 102, and I know the population variance is 144. Well, we said, we've already kind of went past that assumption today. We said we usually don't have the population variance. We usually only have a sample variance, but we can use the standard normal to approximate just like we did have it, okay? So if I'm thinking about building a confidence interval, to get my upper and lower bound, I'm going to take my sample mean, and visually I'm going to subtract to get my lower bound, or add to get my upper bound. The number of standard deviations away I need to get alpha over 2 on either side of my confidence interval, right? Or in either tail, right? Total of alpha in the tails, half of alpha in each tail. We then said we're going to multiply that by the standard deviation. I keep wanting to do X. Sorry, I'm using Y as my notation. of my sample means. Well, here I gave you a population variance, so we can use the Z tables. It's the same kind of thing. The notation would look like this. It's just that instead of a sample variance, I'm using my population variance. But once I plug the numbers in, it'll look no different. So my lower bound would be take the sample mean, subtract this Z value. What's the standard deviation of my sample means? The square root of that population variance over my sample size. So this would be my lower bound. I would then do the exact same thing, but add this many standard deviations. So remember, this really is representing the standard deviation of my sample means, which is the statistic I'm trying to build the confidence interval for. So here's my upper bound. Here's my lower bound. I was told my sample size is 50, variance is 144. I already forgot, was it 102? I found my sample mean. Yeah, right. So I've given these three pieces of information. The only thing I need to do to build that confidence interval is figure out how many standard deviations away do I need to go to build a 99% confidence interval. So we already said earlier, a 99% confidence interval, we said we can kind of think about another term we might start using is that would correspond to what level of significance? Yeah, someone's holding their hand up, just 1%, which this helps us identify what would our alpha be? 0.01. Now, with confidence intervals, it's just like a two-tailed test. So I'm looking for these Z values such that the total area on either side of that many standard deviations is 0.01, which means I only have half of alpha in each tail, or 0.005. Okay. So I might ask you to do confidence intervals on this first quiz. If I do, it would be using the standard normal distribution like this. I won't yet make you use the student t. We can always approximate it using the standard normal. So I'm looking up what Z value gives me 0.005 in either tail. If I was looking this up, since the table is constructed to always give me the area to the left, which one of these is probably going to be easier to find? Probably this guy, right? So, and I'll come back here, but no, I won't. Well, I will, but I hit the wrong thing up here. So we've got, I already closed that Z table, didn't I? I'm going to duplicate this so that we can go to files. We can look at that Z table. So if I have 0.005, that's the area in my tail. So I kind of hunt here, what's closest to that? Looks like it's in between these two values, right? That cumulative probability. So negative 2.57, negative 2.58. We'll use the higher of the two, right? So, sorry, I didn't mean to exit out of the table there. We wanted 0.005, so we're in between these two values. So negative 2.57, negative 2.58. We'll always kind of default to using the higher and absolute value of the two, so negative 2.58. Now, when we're plugging these into our confidence interval calculations, the negative sign's already there, right? So all we really have to plug in here to find our upper and lower bound would be, what was that number of standard deviations? It was 2.58. Now it's just a matter of kind of getting these plugged into our calculator, okay? So if anybody can beat me to it, I'll throw these into Excel real quick. But if anybody beats me to it, let me know. So the lower bound would be what? So 102 minus 2.58 times square root of 144 over 50. So I'm getting what, 97.62? Can anyone verify if you're following along? But that should be right. Yeah. So I'm just typing this into Excel behind the scenes, right? Because this is just a matter of getting this entered into our calculator. Okay. Now, one thing I could do to save myself some time is instead, notice I'm adding and subtracting the same thing to get my upper and lower bound. So instead of calculating my upper and lower bound, what I could do is first calculate this. The term that we're going to use to reference, this is what we call our margin of error, okay? So if I add my margin of error to my sample statistic, my sample mean, I get my upper bound. If I subtract it, I get my lower bound, okay? So if I do that, I get what? I think this is 4.38 approximately. So if I subtract that from 102, I would get my lower bound of what? 102 minus that is 97.62. And if I did 102 plus that 4.38, I get 106.38 rounded to the second decimal. Okay. So what I'm doing that you can't see when I'm referencing these numbers, you can do this in a calculator. I like to use Excel just because I'm somewhat good at it, but also it makes things quicker. All I did was calculate that margin of error in a cell here, right? Just plugging my values in. Once I have my margin of error, and I could change this for any example that I want. Here's my lower bound. Here's my upper bound. How would I find my lower bound? Just take that mean of 102, subtract my margin of error. How would I find the upper bound? Take 102 and add that margin of error. And I could even put 102 in a different cell, reference that, and then for another problem, just update the sample mean that I had. Right? I won't expect you to do that or kind of use Excel, but if you are familiar with it and you like to use it, you could kind of set this up so that really, and this is probably more than I need to do, but like you could do mean, variance, sample size, right? You could then do, what's my margin of error? That would be whatever the number of standard deviations away I needed to go was, times the square root of my variance over my sample size. I could then say my lower and upper bound would just be the mean minus my margin of error, mean plus my margin of error. Now, any example I give you, I could do 105, 150, sample size of 46, and I could find my upper and lower bound for any problem, right? When any sample I find, I just change those three values, right? And this kind of builds me my 99% confidence interval. But for the example we just did, the number that you should put in for the quiz, 97.62 and 106.38 should be that upper and lower bound. Okay. All right. Any questions on that before we kind of move to the next question here? Okay. And I'm not going to ask you about weird, like 96% confidence. I'm going to use those same, the ones that I have the summary of in the slides. We're using those same three values, right? So this number of standard deviations away shouldn't be hard to find. It should always be those same values. Should always be the 10, 5, 1% levels corresponding to 90, 95, 99%. Okay. So what if I did the same thing, but I've got a hypothesis test where I assume the mean is 105, right? I don't care if it's above or below. I've got a two-tailed test. I've just assumed it's equal to this value. Can I reject that assumption? Well, I found the same sample mean, same sample variance, same sample size here. So what is something that I could calculate from this? So what would I compare to a critical value? T value or my test statistic. Once I have my test statistic, I could find the corresponding p-value and use the p-value approach as well. So what is that going to look like for us, right? I'll just kind of write this out in Excel since we have everything. Maybe. Well, I would like to do it in Excel. There we go. Okay. All right. So I've got the same values here. I've got 102, 144, and what, sample size of 50. So I'm going to find my test statistic, right, which was just take my sample mean. We said we're then going to subtract the assumed true value of 105, right? I'm then going to divide that by the square root of my sample variance, which here I gave you a population variance. We're using the standard normal to approximate, so it doesn't matter, right, which one of these we use. In practice, we really will only have a sample variance, but we're using the standard normal to approximate, so it doesn't change anything for us here in this example. Divide by the sample size, and that should give me my test statistic. Now, at this point, I could do one of two things. I could remember, or I could go back to that slide and remember that, okay, for a two-tailed test, for this alpha of 0.1, 0.05, and 0.01, what were my critical values for a two-tailed test? So if we went back, it was positive and negative 1.65, positive, negative 1.96, positive and negative 2.58. Right? I just found a test statistic of, now I already forgot what it was, what, negative 1.77 approximately. So I will reject if the absolute value of my test statistic is greater than the absolute value of my critical value. So is negative 1.77 larger in absolute terms than positive or negative 1.65? Yeah, so I would reject. What about 1.96? Not quite, right? So I would fail to reject. Well, if it's not larger than 1.96, sure isn't larger than 2.58. So what levels could I reject at here? Well, here I've got an alpha of only 0.1. What level of significance would that correspond to? I can only reject at that 10% significance level. Okay. So we're thinking about using the critical value approach. I could do something like this. Now I could also use the p-value approach, right? Same kind of thing. I've got my same three benchmark alphas, right? But here, if I wanted to find my p-value, what am I doing? Well, I'm finding the area to the left of my test statistic. It's a two-tailed test, so I would then need to multiply it by 2. If I go ahead and do this using kind of my standard normal approximations, negative 1.77 would be, it's hard for me to do looking at this. So negative 1.77 was 0.0384, right? So 0.03, oh, sorry. I didn't hit this hard enough. Let's just say I'm getting some confused looks now. I know why. Negative 1.77 would correspond to 0.0384 to the left of it. So this area was 0.0384. If I multiply that by 2, I'm getting something that's, I'm rounding egregiously, but approximately 0.07, right? There's some more decimals there, but for the sake of what we're doing, that's all we need. Why? Because we reject if that p-value is less than alpha. So will I reject at the 10% level? Yes. Would I reject at the 5 and 1? No. The same rejection decisions we would have made using the critical value approach. Okay. So if you're in class today, hopefully this is an easy one. Get another 2 minutes to get it submitted. So hopefully everyone was able to get it pulled open. Click yes to earn just half the points for just being here and responding today. Got another way I can do this. I think I'll make future quizzes easier to earn these base points. They've got a new quiz feature. But really, we could only reject at that 10% level. And then those two values that we had for the upper and lower bound was what? 97.62 and 106.38. Okay. So before you guys get out of here, I didn't quite get through everything I wanted to cover today. So I will make that quiz available. We haven't talked about two-tailed stuff. So one thing I said that won't be true. The thing that's true is you should be able to have all the information to answer those quiz questions. You won't have quite enough information to work on like the last 2 problems of that homework assignment. So we'll definitely get through that first thing on Thursday, and then we'll transition to the next topic, which is going to be linear regression. Okay. So the quiz will pop up after class. You have a week to do it. We've already covered everything. That homework assignment, due date still stays the same. Those last 2 questions, though, we won't cover until next class. Okay, so start working on that early, get it out of the way. Other than that, we'll see you guys on Thursday.